So welcome to our fourth lecture. Today we're going to jump into combinational logic. But before I start, just let me remind you what we covered. We were able to cover RowHammer and memories forget refresh, DRAM refresh as mysteries. Were those interesting to people? Yay, okay, that's good. So now you know some interesting things in computer architecture. There are many, many interesting things, but we don't have time. So if you're really interested in this stuff, this is really an ongoing research topic. As I said, this needs to be fixed and people are really trying hard to fix it. And you can watch more lectures on RowHammer, refresh, which is fascinating, I think. Memory performance attacks, which we unfortunately didn't cover, but you can find lectures online. This is actually a fun thing also. You can attack a computer and reduce its performance significantly by destroying the performance of whatever is running on that computer, on the cloud or anywhere, if you're interested. And one thing I did not cover is Bloom filters, and many of you don't know that. We don't have time to cover that. You may see it in a future class, data structure and algorithms class potentially. But Bloom filters are a great data structure to represent approximate set membership. So if you want to approximately represent a set, and if you're okay with false positives in your queries, Bloom filters are a wonderful structure. It's used in both hardware, software, and co-design systems. And I'd recommend you take a look at Bloom filters. And here's an introduction to Bloom filters only in 15 minutes. But takeaways from the last 3 lectures, if I had to summarize, hopefully in this course, you will think critically and broadly. And I mean that in every aspect of life. You should really think critically in everything you read, everything you see, and everything you work on, I would say. And broadly as well, because broadly enables the solutions that no one else thinks of, right? So I think I've given you a version of the slide in the past. Basically, what are the real takeaways? It's really a great time to be understanding and designing computing architectures because there are many challenging and exciting problems, both at the lower levels of the stack, technology levels, devices. RowHammer is an example. At the architecture level, memory refresh is an example, for example. And at the applications level, we have these really extremely intensive applications that we don't know how to really work with in our computing platforms. And as you see, it's driven by the explosion of data, new applications, ever greater realism, push for many different new things. And we clearly have significant difficulties at the technology layer as well, as we saw with RowHammer, for example. So hopefully you're as excited as I am to go forward. So clearly computer architecture is an enabler of the future, right? And we discussed this multiple times in the lecture. And I'd like to give you another opportunity for extra credits if you're interested. This is going to be very easy actually, because you've seen part of this lecture before, but it says required, but you can watch it and you can do the extra credit and you can get 1% extra credit again in the course. Basically, these are lectures that I normally deliver. One of the lectures is the lecture I delivered when I joined ETH, or a year after I joined ETH. It's my inaugural lecture that talks about a lot of interesting things in computer architecture and what may be coming into the future. You can watch either of the lectures or both, up to you. And again, do an optional assignment like you did with the seminar from Cerebras. What are your key takeaways? What did you learn? What is interesting? What did you like or dislike? Does that sound good? And you get 1% in the entire course. So if you do everything else perfectly in the course, your grade will be 101, for example, if you do this also. Does that make sense? If you do both of the assignments, Sean Cerebras assignment, your grade will be 102. That's the basically impact of these assignments, which I believe is quite high. Okay, as I said in these lectures, there are no real required readings, but these are readings that I would recommend you to do if you really want to supplement your understanding of the lectures. And if you actually do them before the lectures, it becomes easier potentially to understand the lectures better. If you don't understand something in the lecture, you can go to the readings and do some of the readings related to the parts of the readings. And these are the readings that we're going to cover this week, although we're not going to cover everything this week in combinational logic. One of the lectures will be next week. And next week, we're going to cover sequential logic as well as start hardware description language and Verilog at some point. So even though this says this week and next week, we're going to spread it out to 2 weeks, actually. It's not going to be basically within 2 weeks, around March 18th or so, we will cover these chapters. And again, if you have to prioritize one of the readings, prioritize the Harris and Harris book. Okay, clear? And you can find these readings online. Before we go on, I will also mention that this course might look like computer hardware. Hopefully, I've kind of convinced you that that's not the case. you will be, it's not just computer hardware, right? Computer hardware affects everything today. You will be much more capable if you actually master both hardware and software, basically span across the stack. You can develop better software if you know what the hardware looks like and understand it. You can design better hardware if you know what the software may look like going into the future and design the hardware for it. And you can develop a better computing system if you actually know all of it, both of it, meaning hardware and the software and whatever happens in the stack, as we will see that picture again, right? Transformation hierarchy. So basically, we will cover the hardware-software interface and the microarchitecture, and we will focus on trade-offs and how they affect the software. Recall the mysteries we discussed, for example. They're actually affecting the software. RowHammer, something very device level, it's affecting the software, right? And people are trying to solve the problem in software. And example chips and platforms we surveyed in the last 3 lectures, we actually surveyed a lot of different platforms. I'll remind you a little bit of that. And those platforms are designed for software actually to execute, including the Airbus chip that some of you attend the seminar for. But first, we need to start with the fundamentals. And the fundamentals really start at the low level, basically. And why? Of course, you can change the world only if you understand these fundamentals well enough. That's true for basics, but also other things as well. And we're going to talk about past and present dominant paradigms in design, their advantages and shortcomings. Trade-offs are a big focus. And what remains fundamental across generations also. That's really important, I think, to know. And what techniques you can develop to solve new problems as well as old problems. So that brings me to the fundamental concepts. And that's really the beginning of what we will do. And what is a computer, right? We kind of asked this question, it solves our problems. But a computer has 3 key components: computation, communication, and storage and memory. And these components may be organized in different ways. Think about that. And if you look at it pictorially, it kind of looks like this. You have the computing unit, communication unit, and memory and storage unit. Memory and storage systems are relatively separate today. You have a main memory and SSDs, for example, and hard disks and maybe tape later on. But I mean, your computing units may be many also. You may have a CPU, GPU, FPGA, and an accelerator, for example. And communication may be different sort of interconnects that connect these things in. And you can look at this as a micro level, at a single node level, but you can also connect different computers, right? And that becomes your bigger computing system now. And I think this is fascinating, basically. You can keep building computing systems by fundamentally organizing computation, communication, and storage memory in different ways, and building different kinds of computation, communication, and storage and memory units. We'll get back to this picture. This is a picture of von Neumann, John von Neumann, who is essentially the name father of the von Neumann model. And he discusses this computing system in this particular beautiful paper. And we will talk about the von Neumann model later on. Keep that in mind. Yes?
What is the difference in memory and storage?
We will get back to it when we talk about the memory and storage. It's mainly, in today's systems, the main difference is you have a main memory, for example, and it's volatile. It loses its data when you power it off. Whereas storage, it's long-term storage. It doesn't lose the data when you power it off. But this difference may be getting blurred into the future. Okay. Okay, you can actually put pictures over there also. And this is another way. Basically, we will cover all 3 components. Especially, we will focus early on processing, how to do the processing. We'll focus on memory. We'll briefly focus on storage also when we focus on memory. And we'll focus on communication also. You can also think of it as I/O, input-output. And again, recall the transformation hierarchy. We will touch upon many things here, but we will also expand. So let me give you a perspective of what is coming in this entire course. Today, we will start with combinational logic design, and then we will talk about sequential logic design, hardware description languages, timing and verification, and then we will go into these are actual logic level. Today, we'll touch into device a little bit, just as an abstraction layer. And then we'll go into the hardware-software interface, talk about ISA, instruction set architecture, and assembly programming. And then we will talk about a lot of microarchitectures, basically, and also architectures, let's say. You'll see the distinction between them. Lots of different things in architecture. I don't want to read all of this over here, so it's going to be a lot of fun. We will start with very basic processors, and then we will build very complex processors, very close to what is built in these systems today, for example. You will see a lot of fundamental operation principles of CPUs, GPUs, systolic arrays, which are used in machine learning accelerators, for example. And then toward the end of the course, we'll talk a lot about memory, which is critically important also, memory technology and organization. You will learn about memory next Friday in the sequential logic, but we will talk about memory a little bit more at the end of the course. You can see over here. And this will also span all the way to programming language and system software. Virtual memory, for example, is something that's employed in all systems that we use today, and it's very hardware-software cooperative. And these are the processing paradigms we will cover. If you don't know any of these, don't worry. You will know all of these by the end of the lectures where we will cover them. And all of these, I must mention that all of these processing paradigms are employed in existing systems. For example, the systolic array principles are employed in the Cerebras system. They also employ other principles like decoupled access execute, etc., partitioning that we will talk about. Okay. So now let's jump into combinational logic circuits and design. But clearly, before we go into that, we will really start with the building blocks, which is the transistors. And then we'll build logic gates on top of that. How many people know about transistors and how they operate? Okay, a small fraction. How many people do not know? Don't be shy. Not knowing is not something to be shy of. Not learning is something to be shy of, probably. Okay, Boolean algebra. How many people know about Boolean algebra? How many people do not know about Boolean algebra? Okay, there's a small fraction. Don't you learn Boolean algebra and discrete mathematics? Yes or no? Yes, okay. Maybe some people didn't take discrete mathematics or didn't like it. So that's why I'm going to cover Boolean algebra, because there are usually some people who raise their hand when I talk about Boolean algebra. If they know about Boolean, if they don't know about Boolean algebra, but I will probably go relatively quickly in Boolean algebra because probably many of you have seen it in discrete math. It could be a let's say refresher for you. We'll talk about combination logic circuits. How many people know about this? Okay, this is what I expect, very small fraction. How many people do not know about combination logic circuits? Excellent, that's why you're here. And we'll talk about how to use Boolean algebra to represent and minimize reduced combinational logic circuits. And well, if time permits, actually, there are some parts we'll go into if time permits, of course. Well, we're not going to cover everything today, actually. This slide is kind of a lie because we will span this into 2 lectures. Okay, let me give you some pictures, basically. Pictures are always good to motivate, right? These are general purpose microprocessors. We've seen some examples. You can see there are 16 billion transistors on this one. And this is Intel's Alder Lake. It's a relatively new processor. And you can see the complication or complexity of this, right? You can see there are 8 cores here and 8 smaller cores here. There's a media engine, specialized processors, and there are a bunch of other stuff over here that I'm not going to go into. But a lot of this is combinational logic, what we are going to talk about. And all of this is almost all of this is transistors, basically. And I don't know how many transistors are on Intel Alder Lake. Maybe someone can figure that out by looking online, but it's definitely more than tens of billions. So you're looking at tens of billions of transistors right here. FPGAs, this is something that you're going to use in your labs. These are also consist of basic building blocks, transistors again. ASICs, application-specific integrated circuits that we have looked at, TPU, for example, and Cerebras, and this video coding unit by Google. They all consist of transistors again. GPUs consist of transistors. Basically, my point is all of these systems that we use today have some basic building blocks. And you remember this picture that we showed yesterday, right? You have different kinds of systems. They all consist of the same building blocks. And we're going to look at those building blocks. I'm not going to dwell a lot on this slide, basically, because what we're going to, we kind of covered this pictorially yesterday and the previous days. But there are clearly trade-offs between these different designs, right? Microprocessors are easy to program. ASICs are harder to program, and we kind of discussed this. Performance, of course, for a given application that ASIC is designed for, it's much better here. Microprocessors are general purpose. And you can basically come up with other things, like what is it good for? How do you program it exactly? What kind of languages do you use to program? This may change, actually. This is not necessarily. If you have a good compiler, for example, you can use the same language to program all of these. Again, if it requires a good compiler. And there are some main companies that actually, this has changed clearly. For example, recently, Xilinx was bought by AMD and Altera was bought by Intel. So they don't exist anymore, these two companies, at least independently, which is interesting how things are changing. But I will make one point, which is this. We will use Verilog in our labs to learn about how to design a microprocessor on a substrate like FPGAs. That's an interesting thing, right? You're going to use some very low-level hardware description language, which we will talk about, to program FPGAs so that you can imitate the operation of a microprocessor. I find this fascinating. You're basically mixing and matching different things used for in different ways. Okay. So, okay, so my point is really all computers are built upon the same building blocks. And let's start by learning about those building blocks. What are those building blocks? And they're essentially called transistors. Since many of you don't know, let's talk about what those are. Basically, today we have billions of these small and relatively simple structures. They're of nanometer size today, and they're getting smaller and smaller. For example, Intel's Pentium 4 microprocessor 2000, that's 22 years ago, had 42 million MOS transistor. It's called metal oxide semiconductor. I will tell you a little bit more about that in a little bit. Today, 21 years later, Apple M1 Max, 56 billion. So you can see that that's more than 1,000, 3 orders of magnitude basically in 21 years, say 20 years or so. That's a lot of improvement in terms of transistors. And transistors really enable computational and memory capacity. So this lecture, we will learn about how the MOS transistor works as a logic element. I'm not going to go into the voltage and current equations that really make a transistor work. We're not going to go into the device level. We're going to set an abstraction level saying that this is our abstraction level. If you really want to know about how a MOS transistor works, you have to take a microelectronics design class. If you talk about microelectronics design in this lecture, then it's going to be a full 2-semester long lecture, let's say. So we're going to really start with this device level basically today, learn about a particular device that's used in all processors, and talk about how these transistors should be connected to form logic gates in today's technology. In some other technologies, this may be different, but in today's dominant technologies, we have a particular way of connecting these transistors so that they can work the way we want. So basically, and then we're going to talk about how logic gates are interconnected to form the logic units, larger logic units that are needed to construct a computer. Now, there's no best place to put this on. Amazing. And I cannot make it smaller. Okay. Okay, so let's talk about what's a MOS transistor. MOS, as I said, is a metal. It combines basically 3 things. Metal, some conductors, so that you can conduct electricity, pass voltage from one higher place to the lower place. Insulators, these are usually oxides, and semiconductors. I'm not going to go into why you need all of these. Again, that's the subject of a microelectronics design course. If you really want to know how this works, go and take microelectronics design. I'd recommend that, actually. It's a very good way of understanding what really goes on at the lower levels. So we get a transistor that looks like this, basically. Usually, this is the transistor structure. This is real. This is a picture. It's an old one. And usually, you have a source and drain and a gate. And you apply voltage to the gate. And the voltage level that you apply to the gate, this enables the transistor or disables the transistor. Basically, source and drain get connected to each other or become disconnected from each other, depending on the voltage level you apply to the gate and the type of the transistor. This is very important. And that's the idea, basically. This transistor acts as a switch based on the voltage level you apply to the gate and the type of the transistor. That's all you need to know, actually, to build computers after this. Assume that this transistor works and somebody gave it to you. Okay, so we'll talk a little bit more about what I just said, actually, with some examples. So why is this useful? Because we can actually combine these things. We're going to actually have a different picture of this. This is a real picture, but we're going to simplify it with some diagram. We can combine many of these to actually implement simple logic gates, AND, OR, XOR, XNOR. You may have learned about this in discrete mathematics, for example. We're going to build adders, multipliers. Well, we're not going to go into multiplier in this particular lecture, but you will see different decoders, for example, as I discussed yesterday, multiplexers and selectors. And as I said, the electrical properties and how this really works is beyond the scope of what we understand in this course. They're beyond our lowest level of abstraction. Okay, so hopefully, if you're not satisfied with what I said, go and take a microelectronics design course. Now, unfortunately, we had to draw a line somewhere. Okay, but I will give you a little bit more detail because this is important to actually build some logic gates and understand how they work. Because it's not good, actually, in general, to say, okay, this is black magic, right? There's no black magic in the end. There's a reason, physical reasons why these things work. And there are 2 types of metal oxide semiconductor transistors, N-type and P-type. I did not name them, but N-type, you can think of it as kind of negative type. P-type looks like this. Basically, we will distinguish them with this notation. So if you look at N-type, it's similar to what I showed you earlier. Source, it has a source and drain, and you have a gate. You apply voltage to the gate. And if you apply positive voltage, drain and source get connected, and it acts like a wire. P-type, you need to apply negative voltage to the gate to actually enable and make it act like a wire. That's the only difference between the 2 transistors. I mean, there are other differences which we will introduce in a little bit. So they both operate logically, very similar to the way wall switches work. So wall switches, those are wall switches. I don't know. I mean, you all have wall switches at home, right? You push the wall switch and electricity, lights turn on. You push the wall switch and the lights turn off. They may have flips. People call flipping the switch, but I think in Switzerland, you don't have the switches that you flip normally, right? You normally need to press a button. So, okay, let's take a look at how does the transistor work. So think about this as a wall switch that you press and you enable the lights. So you have a power supply, you have a light over here, and you have a wall switch. What do? If you want to turn on the electricity, you go to the wall switch and press it. And for the lamp to grow, electrons must flow from the power supply to the lamp and back to the power supply. That's how you actually get a voltage differential. And in order for the electrons to flow, there must be a closed circuit over here from the power supply to the lamp and back to the power supply, as I said. And the lamp can simply be turned on and off by simply manipulating this wall switch to make or break the closed circuits. So if you press the wall switch, hopefully we're going to press at some point. There you go. If you press the wall switch, this circuit gets connected and the lamp glows because it gets connected to a high voltage power supply and the current flows here and then it goes back to the power supply and you have a closed circuit right now that keeps operating. At some point, you go back and press the wall switch again or flip it back and then electrons stop flowing because you have an open circuit. Basically, you can replace this wall switch with a single transistor. That's it. A transistor is the same as a wall switch from our perspective, so that we can build logic on top of it. Let's take a look at it. So instead of the wall switch, we could use either an N-type or a P-type metal oxide semiconductor transistor to make or break the closed circuit. Let's use an N-type. So this is the schematic of this N-type MOS transistor. I'll call it MOS anymore from now on because metal oxide semiconductor is kind of too wordy, right? As I said earlier, if the gate of this N-type transistor is supplied with a high voltage, the connection from the source to drain acts like a piece of wire, meaning the circuit is closed. If the gate is applied, what you may ask, what is high voltage? In today's technologies, voltages are very low actually. It's closer to 0.3. But depending on the technology generation, the high voltage can range from 0.3 to 3 volts. Today, we're actually at very low voltages, which is good because you will see power consumption a little bit, and power consumption is lower at low voltages. Okay, so that's what you need to know. Well, not only this, but if the gate is applied with a 0 voltage, this is an N-type transistor. If you have 0 voltage over here, then this acts like a closed circuit or a broken circuit. Drain and source are not connected to each other, and the circuit is open. Make sense? So if you apply high voltage, this acts like a switch that you connected, and electricity turns on, voltage flows, current flows. And if you apply 0 voltage to this N-type transistor, lights do not turn on. You can think of it that way also. In fact, I have an animation showing that. Yeah, let's take a look basically. So we have an N-type transistor as a circuit with the battery and the bulb, just like the wall switch earlier. So this is our transistor now, not the wall switch. You go and apply 0 volts, light doesn't turn on because the transistor doesn't conduct current between the source and the drain. This looks like an open wire. You go and apply high voltage. Now the transistor acts like a wire and power supply gets connected to the bulb. As a result, electricity turns on, right? Makes sense. Okay? Basically, the transistor is the wall switch. You can also look at the transistor this way, shorthand notation. You can actually express the circuit using a shorthand that kind of looks like this. You have high voltage, this end of the power supply, and you have low voltage, this end of the power supply. You can think of it as the ground, and this is the highest voltage. And the gate acts between them. In fact, we're going to use this notation soon. And you can replace the light bulb because the light bulbs are not going to be that relevant in our discussion going forward. Does that make sense? Okay, good. So because this is really the fundamentals. After this, we're going to build everything on top of this. And the P-type transistor, okay, this was N-type. Now I'm going to confuse you a little bit. P-type works exactly the same way, well, except with opposite voltage levels. I should say it that way. So this was the N-type transistor. In order to make it a closed circuit, you need to apply high voltage. P-type transistor, in order to make it a closed circuit, you apply low voltage to it. So if you apply 0 volts to it, it acts like a wire. Makes sense, right? You may ask, why do you have these two different types of transistors? Well, that goes into the lower level. Because these transistors work best in different ways. So for example, N-type transistors are good at conducting high voltage. P-type transistor, they're not good at conducting low voltage. That's why you need to actually connect them to the high voltage. P-type transistors are not good at conducting high voltage. They're good at conducting low voltage. That's why these transistors need to be mixed together in a circuit. That's why we have both of them. You may ask the question, why don't we have just N-type and P-type? That's the reason, basically. There's a lower level reason for that, and we will see that in a little bit. Okay, hopefully that makes sense. Okay, now let's construct some logic gates from these things. No. So this is clearly, now we're going one level higher in the abstraction. We know transistors. Transistors actually act like a logical switch. How do we build logic structures out of these MOS transistors? And we're going to construct basic logical units. Now we're going to go one level up in the hierarchy. And these are called logic gates, basically. You can call them logical units because I call them logical units because they act based on the principles of logic, right? You've taken discrete math. You know about Boolean logic. We're going to see that again. They basically operate based on those principles of logic. These are things that implement those principles. Okay, so as I said, they implement simple Boolean functions. And if you're interested in Boolean logic, this is really what Boole introduced in 1847, the mathematical analysis logic. We're going to get back to that in a little bit. Okay, so how do you make logic blocks using CMOS technology? Now I introduced another term, CMOS. MOS was metal oxide semiconductor. C is complementary, meaning you have to have both P and N type. And you have to use them in a complementary fashion. Let's see what I mean, really. Well, I think I said this already. Modern computers use both N-type and P-type using CMOS technology. And NMOS plus PMOS is CMOS. And let's take a look at the simplest logic structure that exists in a modern computer. I'm going to throw you two transistors connected this way. So what does this look like? Basically, you have a P-type transistor over here. You have an N-type transistor over here, right? And P-type transistor is connected to 3 volts, and N-type transistor is connected to 0 volts over here. Input is tied to both of the transistors' gates, and then output is the output. Okay, so let's see what happens over here. Okay, I don't remember if I said this correctly last time, but P-type transistors are good at conducting high voltage. N-type transistors are good at conducting low voltage. We call it pull up and pull down. That's why you put them in a complementary way like this. Make sense? And why are they good at conducting high voltage versus low voltage? Well, that's beyond our abstraction level again. That's basically the characteristics of the transistors themselves, how they're built and how they react to different input voltages when the different gate voltages when there are different kind of voltages on their source and drain. And there's a lot of field studies that happen on that topic. So if I ask you, what does the circuit do? What would your answer be? I have one. It's a NOT gate. Does anybody know what a NOT gate is? Yes, in the back. Exactly. It's an inverter, basically. It's the gate that inverts the input. What does this mean? If the input value is 0, you get a high voltage at the end. If the input value is high voltage, you get low voltage or 0 voltage at the end. Let's take a look at how that works. So let's take a look at what happens when the input is connected to 0 volt first. You can test it, right? Because we know the principles right now. You go and apply low voltage to both of these transistors. And if you apply low voltage to the transistor over here, this is P-type, it acts like a wire. So 3 volts get connected to the output. This transistor acts like an open circuit because it doesn't get turned on. This is NMOS, remember? And as a result, the circuit looks like this. Transistor has a switch. This switch is turned on. The switch is turned off. So 3 volts gets connected to the output Y, and output is now 3 volts. Makes sense, right? So basically, you kind of inverted the input. Now, if you apply 3 volts, okay, basically P-type transistor pulls the output up. So P-type transistors are actually good at pulling up the voltage. This may be, I kind of use this, P is good at pulling up, right? That's how you remember these things sometimes. And it's easy to forget, even if you know exactly how they operate. At some abstraction level, you need some ways of remembering things. So p-types are good at pulling up, they're terrible at pulling down. That's why they're always connected to the top over here where you have high voltage, as we will see. Okay, let's take a look at what happens when the input is connected to 3 volts. We're assuming that 3 volts is the highest voltage in our system. But there may be, the highest voltage may be 1 volt or 0.8 volts. Then you need to change this 3 volt to that level. Okay, so you go and apply 3 volts to the gates of these transistors. And let's take a look at what happens. Basically, if you apply 3 volts to the PMOS transistor, it acts like a broken circuit, closed circuit, open circuit, sorry. So this wire doesn't get connected. You apply 3 volts to the NMOS transistor, this wire gets connected. As a result, 0 volts get connected to the output and output becomes 0. Basically, the switches, transistors as switches look like this. And N-type transistor right now pulls down the output. Basically, it's connected to 0 volts ground and it's pulling down the output line over here. Hopefully it makes sense. And N-type transistors are good at pulling down the voltage. And you can again remember this as N is good at pulling down at the end, right? Okay, so now we built an inverter. This is how you can build a logical inverter. You apply high voltage, you get low voltage at the end. You apply low voltage, you get high voltage at the end, at the output. This is also called a NOT gate. And you can see that this is a CMOS technology. You may come up with some different transistor technology. It may work differently, but that's out of the boundaries of this class, right? You go take microelectronics design, you see different transistor technologies potentially. Unfortunately, none of those transistor technologies are employed in today's systems. Today, we use CMOS technology. People are investigating emerging technologies because potentially CMOS technology is running out of steam, let's say, because we've reduced the size of the transistor so much. We're going to talk about Moore's law in a little bit. That these transistors may not be working perfectly anymore, as we discussed in earlier lectures. But still, we're using CMOS technology and we're pushing the boundaries of the CMOS technology. Okay, why do we call it NOTs? I mean, this is obvious, hopefully. If you apply low voltage, you get high voltage in the output. If you apply high voltage in the input, you get low voltage at the output. That's why it's inverting. And CMOS is also inverting logic. Basically, you build everything by inversion. You will see that when we build an AND gate soon. So this is basically now. Actually, let's make it a little bit more abstract. Let's not talk about voltages also. Let's talk about logic. Let's assume that 0 volts represents a binary value of 0, and 3 volts represents a binary value of 1. Now this is really a logic gate, right? You can put a truth table to it. A is our input. It can be 0 or 1, 0 volts or 3 volts. And based on the input, you get different values in the output logically. So if A is 0, P is on, N is off, as we discussed earlier, Y becomes 1, meaning 3 volts. But we're going to ignore the volts from now on. We're going to build the next abstraction level logic. If A is 1, P is off, N is on, and Y is 0. This is our logic circuit now, right? Now we don't need to know anything about voltages. I don't care about voltages. Whatever voltage you apply, make sure you apply it correctly. When I apply 0, make sure you apply the voltage level of 0 correctly. When I apply 1, make sure you apply, when I say 1, make sure you apply the correct voltage level. I just want to get the result that looks like this. And that's our abstraction level of a NOT gate right now, right? Unfortunately, this somehow doesn't appear. I tried very hard to make sure it appears, but it's not appearing for some reason. There's a bug in PowerPoint. But basically, Y is equal to A bar, not A, in other words. So it appears better over here. So Y is equal to A bar, as you can see. And we represent it abstractly like this. This is an inverter. This is the representation of an inverter in logic gate terminology, or logic gate schematics, let's say, pictorially. That looks nice. Now, this gives me an abstraction level. I don't need to think about these transistors. Somebody implements those transistors. Great. Hopefully, they make it work. I just care about the logical functionality. Y equals A bar. Okay, I already said this. We call it a NOT gate or an inverter. And every logic gate has a truth table, which shows that it is, which shows what is the logical output of the circuit or gate for each possible input. You learned about truth tables? Okay, so who doesn't know about truth tables? I'm curious. Okay, everybody knows about truth tables. That's good. So this is one of the simplest truth tables you can get, right? This is the input A. This is the output Y, and If A is 0, you get 1 in the output. If A is 1, you get 0 in the output. And the truth table size definitely depends on how many inputs you have, right? You have one input here. So because we use binary logic over here, you have 2 lines, 2 to the 1 lines. If you have n inputs, you'll have 2 to the n lines in the truth table. So if you have a 1,000 input circuit, this truth table becomes 2 to the 1,000, which is huge. So we're going to do something about expressing functions later on so that we don't need to write these huge truth tables going into the future. And that's where the Boolean logic also comes in, but we're going to even try to make Boolean logic simpler to express. Okay, let's take a look at another CMOS gate. I'll ask you the question. Let's build a little bit more complex gates. So what is this? Maybe you can think of this a little bit. I kind of threw something at you. So let me help you a little bit. You have 2 inputs, A and B. You have 2 PMOS transistors in parallel connected to the output. And you have 2 NMOS transistors in series, serially connected to the output, as you can see. And input B is applied, input A is applied to 1 PMOS transistor and 1 NMOS transistor over here. And input B is applied to 1 PMOS transistor and 1 NMOS transistor over here. Have you figured out what it does? Okay, you go first. It's an AND gate. Okay. 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 So far, none of you are correct. Okay. Okay, what does NAND do? Okay, yes, that's the correct answer. It's a NAND gate. Yes, it may look kind of tricky. You will get used to it, but it is a NAND gate, basically. Okay, let's take a look at how it operates, basically. You need to go through how it operates, and it may not be easy to do this if you're doing this for the first time when you look at it, right? You need to, so let's take a look at it. So input A and B can be zeros, right? So this is the truth table. Let's build a truth table for this. That's how you figure out what this is. So I already gave you a NAND gate. Actually, your colleague was right. So if A and B are both zeros, let's take a look at what happens first. You need to enumerate all cases. You have 2 inputs, so you have 2 to the 2 lines. And let's enumerate the first case. A and B are both 0. So P1 gets a 0 over here. So what does that mean? This is a PMOS transistor, so it gets enabled, right? So 3 volts get connected to the output. And then N1 gets disabled. So output clearly does not get connected to 0 volts. So I think we know what is happening right now, right? But let's make sure what happens. So basically, output gets connected to 3 volts when we have 0, 0. And it doesn't get connected to 0 volts. Let's take a look at the second, just for verification, right? B is 0. So this one also gets enabled. So 3 volts gets connected from this path as well to the output. And this gets disabled because this is NMOS transistor and you're applying low voltage to it, 0 to it. So these are turned off, both of them. These are turned on, both of them. As a result, you get a 1, meaning 3 volts at the end. So when the inputs are 0, 0, you get both transistors on and you get both transistors off over here. You can think of it, you can add more structure to it, right? Maybe I will get to this later. Let's take a look at another input. Let's take a look at 0, 1 over here. A is 0, meaning that this is enabled. This is disabled. B is 1. This is disabled. And this is enabled. But it doesn't matter if this is enabled because this is disabled. This is still an open circuit. So output doesn't get connected to 0. And because this gets connected to the output, you get, again, 3 volts at the end. So if you have 0, 1, P1 is on. Even though N2 is on, it doesn't matter because N1 has to be on also so that output gets connected to the lower level, or the lower voltage level. So if A and B are like this, you get still 1 at the end, 3 volts. Again, let's take a look at, just to be complete, if A is 1, B is 0, something similar happens. This time, this gets, A is 1, this is disabled. This is enabled, interesting. We cannot tell anything right now. If B is 0, this gets enabled, so output gets connected to 3 volts, and this gets disabled, so output doesn't get connected to 0 volts. So you again get a 1 at the end. Now, the interesting thing is when both are 1, if both of them are 1, A is 1, this gets disabled, this gets enabled, B is 1, this gets disabled, so we know now that output doesn't get connected to 3 volts, and this gets enabled, so output gets connected to 0 volts. But that's the only case where you get 0 at the end. And if you look at this, this is the inverted AND. The Y output becomes 0 only if A and B are 1. So in an AND gate, output becomes 0, output becomes 1 only if A and B are 1. This is an AND gate, output is 0. It's not of an AND basically, right? Inverted AND. So of course, we analyzed every single case over here. That's one way of doing it. But then you can also realize what's going on in the circuit, right? So if you look over here, P1 and P2 are in parallel, meaning if any of them are connected to the output, they should pull the output up to 3 volts. So basically, in parallel transistors like this, only one must be on to pull the output up to the 3 volts. And in series, both of them, N1 and N2 are connected in series, both must be on to pull the output down to 0 volts. And if you see that structure in the circuit, then you easily say that, oh, this circuit gets turned on if either A and B is either A or B is 1, meaning turned on, output becomes 3 volts, and output becomes 0 volts if both A and B are 1. So that's another way of analyzing the circuit by using the series and parallel structure, right? So hopefully that's clear. You can analyze the circuit in multiple ways. And this is how we express an AND gate. This is a Boolean logic, A and B complemented. Or you get, usually we don't represent the dot. That dot means AND operation in Boolean logic. We don't represent the dot, basically AB complemented. And this is our basic NAND gate right now. Looks great, right? Everybody's okay with it, this analysis? Okay, good. Okay, and this is how we represent it in a schematic way. And this is actually, this bubble always means it's inverted. If this bubble doesn't exist, then this is an AND gate. But because of this bubble, it's a NAND gate right now. Y is equal to NAND of A and B. We're going to see the AND gate also. And this is a truth table, basically. I kind of showed you the truth table over here. But of course, I looked at the internals also. Logically, you don't look at the internals. You just look at the logical output, right? And logical output is, this is the AND gate, truth table of an NAND gate. Okay, so how do you build an AND gate now? Maybe that's a tough question for you. Anybody who wants to venture? I guess. Okay, you didn't speak so far. Maybe you can say. Exactly. Yeah. Basically, you have this NAND gate already. Why don't you put an inverter at the end? So this is our AND gate function. That's the Boolean equation, A and B. And this is the logic schematic. And this is the transistor level implementation. This is our NAND gate. And basically, we know that AND is inverted NAND. And you take the complement using an inverter. We know how the inverter operates, right? Make sense? Can someone do better? You can try to do better, but if you do better, you're going to violate the operational principles of the transistors. Meaning, if you can come up with a circuit that may provide an AND to me, and I can do it for you, but I'm not going to do it right now. You can think about it. But you have to put the NMOS transistors up and PMOS transistors down, and that's not going to work in CMOS technology. Make sense? Basically, in CMOS technology, PMOS transistors are good conductors of high voltage. They're very poor conductors of low voltage. If you put them down, they're not going to pull down the circuit because they don't work that way. That's the operational principles of PMOS and NMOS transistors. Okay, so basically we make an AND gate using one NAND gate and one NOT gate. And that's the downside of this technology. You need to use 6 transistors to make it happen in CMOS. If you had some other transistor technology, maybe you could do better. Now let's take a look at the summary, basically. So this was the NOT gate, right? Looks nice. This is our NAND gate. Looks nice. Truth table. So schematic, truth table, transistor level implementation in CMOS. And this is hopefully coming. Yeah, it's coming slowly. I'm going to put this somewhere over here. Okay. This is our AND gate. This is the schematic, truth table, transistor level implementation, and CMOS. So let's talk about the general CMOS gate structure, and then we'll take a break. So basically, this is the general form used to construct any inverting logic case, such as NOT, NAND, and NOR, looks like this. You have some inputs. You apply the same inputs to a PMOS pull-up network and MMOS pull-down network. So if you go back, you can think of this higher part as a network, right? This is the PMOS transistors, let's say. This is NMOS transistors. And PMOS transistors are in parallel, NMOS transistors are in series here, in this particular case. You can do it the other way around also. So the networks may consist of transistors in series or in parallel. When transistors are in parallel, the network is on if only one of the transistors is on. When the transistors are in series, the network is on only if all the transistors are on, right? So these transistors can be in parallel, these transistors can be in series, or the other way around. If you do the other way around, you actually get an OR gate. So if you actually do what I said over here, instead of these N transistors to be in series, you make them in parallel and connect them to the output. You make the P transistors in series and you connect them to the output, you'll get an OR gate, basically. That'll be an OR gate. Think about it. You'll see it in your readings also and later on as well. But this is the general structure. It's very easy to do it. The key thing you should not forget is PMOS transistors are used for pull-up, NMOS transistors are used for pull-down, and you should not violate this. Okay, so clearly, if for this to work, exactly one network should be on and the other network should be off at a given time. So both cannot be on, meaning both cannot be turned on. Why? Because if both networks are on at the same time, there's a short circuit, right? Meaning 3 volts get connected to the output, 0 volts also get connected to the output. So what do? Everything gets connected to the output. So what you have as the result is incorrect operation in the end. If both networks are off, so this is not a wire, they're not connected. 3 volts is not connected to the output. 0 volts also is not connected to the output. Then you don't know what you get in the output, right? That is called floating. We will see this term later on also. Basically, the value of the output is undefined. You have no idea what. So keep this in mind. If you connect 3 volts and 0 volts to the output at the same time, you're doing something wrong. You're violating the circuit principles, basically. So as a result, you get incorrect operation. Sometimes you may even burn the circuit potentially. If you're not connecting to anything to the output, then you're not necessarily doing something wrong, but you don't know what the output is in that case. Right? Okay. So let's dig a little bit deeper. Why do we have the structure? Because, as I said, most transistors are not perfect switches. So we're using this abstraction, but they're not perfect switches underneath. So as I said, PMOS transistors pass ones very well, high voltage very well, but zeros poorly. NMOS transistors pass zeros very well, but ones very poorly. As a result, they should be used where they are good at. So basically, PMOS transistors are good at pulling up the output. They are connected to 3 volts. NMOS transistors are good at pulling down the output. They're connected to 0 volts. That's why NMOS transistors are always connected to 0 volts and PMOS transistors are always connected to 3 volts. And that's why we have the structure. PMOS is always up here, NMOS is always down here. Again, this is based on how transistors operate. If you really want to know a little bit more about this, you should read section 1.7 in the Harris and Harris book. They don't go into a lot of detail, but this is how it is. This is life, basically. We don't have perfect transistors. Okay, so maybe this is a good place to actually take a break. I'll dig a little bit deeper, and then we're going to talk about Moore's law and Boolean logic. All right, let's get started, or let's continue from where we left off. Hopefully you remember this picture. Basically, in CMOS, we have this pull-up network that's made of PMOS and pull-down network that's made of NMOS. And hopefully it's clear to you right now that why PMOS is here and why NMOS is here. You don't need to worry about it too much in this course going forward, but this is for you to really know what's going on underneath in CMOS. But let's take a look at some other issues, because these issues are going to be important in the future. Latency. Basically, latency means how long it takes for the output to become 1 or 0 given an input, right? So which one's faster is one good question, right? Are transistors in series faster, or are transistors in parallel faster? Any takers? Yes? Parallel, yes. So parallel is the right answer, because if you have transistors in parallel, you can see that the connection, so these 2 transistors are in parallel, and the connection from the higher voltage to output is only 1 transistor, right? Only 1 transistor needs to be turned on. You could keep adding parallel transistors, 10,000 of them, let's say, I just made it up. You have to go through only 1 transistor to pull up the output. But if the transistors are in series, you have to go through 2 transistors, and 2 transistors need to turn on, and the wire is longer, as you can see, so that the output or this intermediate output gets connected to the lower voltage in this particular case. And imagine you add 10,000 transistors in series. Now that becomes a problem, right? So basically, transistors in parallel are faster than transistors in series, or this says the opposite over. This says the same thing in an opposite way, as you can see, because you have more resistance on the wire if you connect many transistors to the wire, basically, and that's the main reason. So how do you alleviate this latency? Basically, you try to not have a lot of transistors in series, and this kind of limits the number of inputs you can have in a gate. And this is real, because this is a real constraint. That's one way of alleviating the latency. Have gates with smaller number of inputs. If you want to have a 10 input AND gate or 10 input NAND gate, you will have 10 transistors in series, right? And don't do that, basically. Use 2 input AND gates, for example, 2 input NAND gates in your designs, or maybe 3 input, right? You need to basically characterize your systems to understand how big of gates you can actually build to satisfy some amount of latency. Why does latency matter? We will see that actually in the timing and verification lecture in lecture 8. Today is lecture 4, so 4 lectures later, we'll talk about timing and verification. We will see how to analyze the timing. Okay, there are other ways to alleviate the latency that talks about pseudo NMOS logic. I'm not going to go into, but it kind of looks like this. So this is a pseudo NMOS 4-input NOR gate. So NOR gate has NMOS transistors connected in parallel. Normally, you would have 4 PMOS transistors connected in series to enable a 4-input NOR gate. But there are some tricks you can play at the lower level and have a very weak PMOS transistor. And weak PMOS transistor can replace 4 PMOS transistors in series. Again, I don't want to talk about it in detail, but you can basically, the key takeaway is you can play some tricks at the transistor level to reduce latencies. Again, those are beyond the scope of this course. But imagine that you can actually play a lot of tricks at the transistor level. So there's a lot more room at the bottom, as I said earlier, at the transistor level. And one example is in your Harris and Harris book. Okay, let's talk about power consumption. This is important because power is, as you know, one of the bigger limiters, energy and power. And there are usually 2 aspects of power consumption. One is dynamic, when the circuit is switching, basically. When you apply some input and the input changes, you consume some dynamic power. And you also consume some static power when the circuit is not doing anything. So for example, this my cell phone over here is not doing anything. Well, I hope it's not doing anything, but assume it's not doing anything. It's still consuming power. It's leaking. As we discussed, the DRAM is leaking, for example, but other circuits are also leaking. So basically, you're losing some values, and then you need to refresh them. But sometimes you're not even losing the values because you don't need to switch the circuits. But even then, there's leakage from the high voltage path to the low voltage path that's consuming power. That's static power. Let's talk about dynamic power. When you apply some input, you basically cause power consumption. This is actually the bigger chunk of power consumption in general, because we know how to actually keep the static power consumption somewhat under control. We don't know it very well in DRAM, for example, but somewhat we know it in some other circuits. Let's talk about the dynamic, yeah. So has anyone seen this equation before? CV square F? Okay, only 1 or 2 people. Again, you don't need to know this for the exam. This is just for your benefit. This is the dynamic power consumption equation. Let's take a look at what this means. C is the capacitance of the circuit. It could be a logic gate. It could be the entire processor that is being turned on and off. It depends on the granularity of analysis, basically. So capacitance becomes higher as you have more transistors connected to the circuit, and as the transistors are bigger, for example, and also wires. Supply voltage is how big your voltage is. So 3 volts, as you can see, there's a quadratic relationship between power consumption and the voltage square. And F is the charging frequency of the capacitor, how fast you're charging or discharging the capacitor, essentially. This is very much related to the frequency that we will see later on. So basically, it's a multiplication of these 3 factors. So if your circuit is big, it consists of big capacitors. If your supply voltage is high, if you're charging frequently and discharging frequently, then you're consuming a lot more power than otherwise. And you can see that voltage is actually squared. So that's why people want low voltage circuits. If you have low voltage, then your power consumption goes down quadratically. In fact, there's an indirect relationship between, well, maybe I should say a direct relationship over here. The frequency of charging and discharging the capacitors depend on the voltage. As you reduce the voltage, the frequency of charging and discharging also reduces. So you can think of frequency as being proportional to voltage as well. So basically, if you want to really reduce your power consumption, you reduce voltage, which reduces frequency, and you have a cubic reduction in power consumption. So if you want to design very low power circuits, voltage is a big parameter. But don't forget the capacitance over here, because this capacitance really determines how big your circuit is. So if you use, for example, high capacitance transistors, that's not going to work very well. High capacitance wires, again, they consume a lot of power. Okay, static power consumption, as I said, is power that's consumed when you're not even touching the circuit. You don't apply any inputs. For example, that's what's happening to the cell phone right now. And you can see that as voltage times leakage power. There's a leakage current. Sorry, this is a leakage current. Basically, there's some small amount of current that flows through the high voltage terminal to the low voltage terminal, because nothing is perfect. As I said earlier, transistors look like perfect, but they're not perfect. Well, let's go back to this picture over here. At least one of them. Yeah, for example, here you have 3 volts, you have 0 volts. You don't change anything. Nothing is changing over here. Even if these are not connected, meaning these are not closed circuits, there's some voltage, there's some current that flows from the input to the output and also through here. Very little current. That's the static current, basically. And that basically causes you to consume some power that's proportional to the current, and you multiply it with the voltage. That's the idea. Keep that in mind. Basically, if your circuit is huge, and if you somehow have components that are not perfectly manufactured or well manufactured, this leakage current could be high. But if your supply voltage is very low, then it's still good. Basically, you can see that voltage really is important in reducing both static and dynamic power consumption. Okay, what is energy consumption? Hopefully, many of you can answer this question. What is energy? Anybody? Yes? Well, it's based on electron movement, but in terms of power, how would you get the energy of a system? Power times time, exactly. Basically, you integrate power over time, right? Well, it's over here. So basically, energy is how much time you spend. And basically, there's a power curve. You're spending some power, and you integrate that power curve over time, and that's the energy you spend. And clearly, energy affects your battery life, for example, right? If I want a battery life over here, I want to use less power, and time I cannot control, I guess, right? At some point, your battery life will be exhausted if power times time is greater than the energy that can be supplied by your battery, right? Okay, so for more information, Harris again has some information related to this. It's not really something that I ask about, but I think this is important to know if you really want to build real systems. Okay, so basically, we've kind of covered logic gates. We didn't cover every structure over here. For example, this is an inverter. There's a buffer also. This basically passes the current exactly. Basically, it doesn't have a logical function. It doesn't change the logical value, but it amplifies the voltage, because as you travel, as voltage travels through long wires, as electrons travel through long wires, there's resistance on the wires. So basically, you lose strength. You lose signal strength, essentially. So you need to use amplifiers. I should call, maybe this should be called better amplifier. It's also called a buffer. It really amplifies the voltage. That's the idea over here. It doesn't change the logical value. Inverter is really the opposite of it. It inverts the voltage, essentially. AND gate we discussed, NAND gate we discussed, OR gate and NOR gates we kind of discussed, even though I didn't show you structures. You can easily do these. XOR gate is interesting. Have people used XOR gates before, or XOR functions? No one? Some few people? Well, this is an important function, actually. What it does is it basically, the output is 1 if an even number of inputs is 1. The output is 0 if an odd number of inputs is 0. So you can see over here, we have 2 input XOR gate. Wait a second. Output is, okay, let me put it that way. Again, output is 1 if an odd number of inputs are 1. Output is 0 if an even number of inputs are 1. Okay, so I got it better right now. So if you look at here, A and B, only in these 2 cases, an even number of inputs is 1. So the output is 1. when A and B are both zeros and ones, the output is 0, essentially. That's the idea. If you can generalize XOR gate, yes. You can think of it that way also, yes. Yeah, that's another mathematical way of thinking it, yes. Yeah, basically you can, yeah, that's the XOR gate. You will see multiple inputs over here later also. So XNOR is clearly the NOT of XOR, right? Okay, and you can build more gates. We're going to build more gates actually later in the lecture. Maybe not today, we'll see, depending on how fast we go on the Boolean logic, but probably not today, basically. But let's take a look at larger gates. So this is a larger 3-input NAND gate. We saw the 2-input NAND gate. We didn't have an extra transistor over here and over here. If you want to build a 3-input NAND gate, it's easy, except you have longer latency in the series path, as we discussed, right? So basically, we can extend the gates to more than 2 inputs. You can have a 3-input AND gate, 10-input NOR gates. You can draw 10,000 input gates, but they may not work the way you really like them to work, of course, right? So there is a limit, basically. If you really want to build gates, you don't want to go too large because they become slower because of the series path and also non-idealities in the circuit. And readings actually have some more examples. You can take a look. Any questions so far? So now we've covered some basics. Now you can build any logic gate, in my opinion, based on those basics. We'll talk about functional completeness, basically. You can actually build any logic gate just using NAND gates. And we will kind of see that later. Have you seen that before? Functional completeness, the concept of Boolean completeness? Anybody? Discrete math? You kind of, who saw it in discrete math or anywhere? Functional complete means basically you can build any function, any Boolean function using a particular gate. And NAND is a functionally complete gate, basically. You can build any function using just NAND gates. NOR is also like that. NOT is not like that. You cannot build any function using NOT. You have to use NOT and AND, for example. Okay, that builds an AND, essentially. Okay, so we will see that notion later on, not today, probably tomorrow. Okay, but let me take an aside a little bit because this is interesting. I mean, how many people know about Moore's law? How many people do not know about Moore's law? Okay, some people, so we'll cover it at some speed. So Moore's law is really the observation that we can keep increasing the number of transistors we can put on a chip and they're still economical. It's just an empirical observation. It's not really a physical law, right? Let's take a look. So this is an older version of it. Moore wrote this paper in 1965. Basically, he observed that component counts that you can put on an integrated circuit double every other year. It's an exponential trend, basically, that he observed, which is nice. It's an exponential because you can see that the y-axis is in logarithmic scale over here. And this is 2005. If you go further, and this is the original Moore paper, basically. It goes from 1960 to 65, essentially, and he projects that this is going to continue. And this has been continuing for a long time. And in fact, in the Cerebras talk, Sean Lee said that Moore's law is well and alive, right? We don't know when it will end, but maybe it's slowing down a little bit, but it's still going on. This is amazing because this enables us to put many, many more transistors on a single chip, single integrated circuit, and it enables us to do more in a single integrated circuit. And he also looked at this, for example. It's an interesting example from his paper, this number of components per integrated circuit. And this is a relative manufacturing cost per component. You can see that there's a sweet spot in 1962 over here, 1965 over here, 1970 expected to be over here. So basically, number of components is increasing and the cost per component is decreasing at the same time. So this is an economic, I would say that this is a law of economics. It's definitely not a physical law. Economically, we're able to manufacture more components on a chip that become cheaper every generation. Okay, and this is until 2011, and you can see Moore over here. He was one of the co-founders of Intel. And again, this curve fits. And this is 2016, and this is the best I could find that's recent. There's no one that has 2021 or 2022, but you can see that the curve is kind of fitting still. I didn't do the exact curve fit, but maybe we're having some difficulties sometimes to achieve it, but it looks pretty linear still. Linear curve on a log scale, y-axis means an exponential increase, right? That's important. Okay, Okay, why am I telling you this? Because I'd like to recommend the reading also with Moore's. Maybe at some point I will ask you to analyze this, not today. I think in the past we kind of asked you to analyze this sort of fundamental paper. It's a very fundamental paper. You can see that it's almost 60 years ago it was written. It's only 3 pages. And this is one quote: with unit cost falling as the number of components per circuit rises, by 1975, economics may dictate squeezing as many as 65,000 components on a single silicon chip, 65,000 transistors. Where are we today? 50 billion and plus, right? If you look at Cerebras, of course, it's trillions, right? Not billions. I don't know what the number is over there, actually. I don't remember. Well, maybe we'll see it soon, but I don't remember, frankly. Another quote: will it be possible to, from the same paper, this is forward-looking, right? Will it be possible to remove the heat generated by tens of thousands of components in a single chip, single silicon chip? Again, today we're at billions and we're able to remove the heat, but it is becoming difficult. So keep in mind, these are the visionaries who have really enabled this sort of growth. Gordon Moore was definitely a visionary by founding Intel. He's enabled this sort of growth, and a lot of people actually made sure this Moore's law continues. And people are still trying to continue this, as you see with the current chips. But at some point, it's going to become extremely difficult, right? At some point, how small can you make a transistor? It's good to ask this question. What are the physical limits? Today, we're at nanometers, right? How many fractions of a nanometer can you get? How many atoms do you need to make the transistor really work? It's good to ask these questions. They're below the abstraction level of this course. But this course and everything else in computing also depends on this, right? What happens if Moore's law ends? Well, actually, everything else in computing becomes even more important potentially. You need to have much more efficient systems, efficient architectures, efficient algorithms. But maybe we really don't want Moore's law to end. We still want, because we have a lot of problems to solve, right? So, okay, how do we keep Moore's law basically? This is really the cutting edge of innovation, I would say, that enables everything else in computing. Maybe if Moore's law ends, we become much more efficient in what we do. We don't use all of these high power languages that waste a lot of power, right? And I think a lot of people at the software level don't care about power, but it has huge implications on the world in the end. Let's talk about how they keep Moore's law. Clearly, it has been enabled by manufacturing smaller transistors and smaller structures. It's not easy. Some structures are already a few atoms in size today. It has been also enabled by finding materials with better properties. You can see that material science goes into it. This is completely different from computer science, computer engineering, electrical engineering. We're talking about material science. And manufacturing is also, it's applied physics and also electrical engineering, right? We're talking about a lot of fields coming together over here. So you can use copper instead of aluminum, for example, better conductor, and hafnium oxide, air for insulators. There are many other technologies that you can use. You saw some of them in Cerebras also, Shanli mentioned in his talk. And one of the challenges, it's not the only challenge, but making sure all materials are compatible with each other. Enabling precision manufacturing. Again, this is a lot of different scientific fields and engineering fields combined together. Because today what's used is extreme ultraviolet light. I think we discussed this briefly. It's called EUV. If you really want to pattern very small structures, these transistors are 10 nanometers. And you need to etch them on silicon. So you have the silicon wafer, and you need to create transistors on it. How do you do that? Well, there are machines that actually pattern those things in transistors using some masks. But the machine needs to be extremely high precision. We're talking about angstroms, very small numbers, right? Nanometers, less than 10 nanometers. Today, we're at almost 5 nanometers today, right? So people have developed machines. Unfortunately, I don't have a picture. I should have probably shown a picture of that machine, which is amazing, I think. But maybe at the beginning of next lecture, I will show it. You have these extreme ultraviolet light that gets patterned on a silicon to really enable these structures. And in the end, creating new device technologies also helps. Better transistors, for example. Today, we have transistors. I'm not going to go into what these are. You can read about them. FinFET, for example, gate-all-around single electron transistors. They work, some of them are used actually. FinFETs are very commonly used. Gate-all-arounds are being used. Single electron, I don't know what the status is at this point. But these new transistor technologies also enable many more transistors as well. So you can see that there's a lot of sweat, blood, and tears that goes into manufacturing these chips that can extend the Moore's law. but we'll see where it goes. It's not dead yet. You may hear it's dead, but as you also heard from Srinivas, it's not dead yet. Okay, and I believe actually people will innovate significantly going into the future at the bottom layer. Okay, so basically innovation at the bottom really enables computing over here. That's what we've been talking about with Moore's law. And remember, I'm not going to go through Richard Feynman's talk again, but Richard Feynman actually, let's say, prophesized this, right? In 1959, when he delivered this lecture, he said, there's plenty of things we can do if we can manipulate individual atoms. And we're at that point right now. Okay, now let's go into, with that aside, which hopefully gave you a more relaxed timing, let's talk about combinational logic circuits a little bit more. Now we can build logic circuits because we have the basic components: NOT gate, AND gates, NAND gate, NOR gate, XOR gate. Let's build things. We understand the workings. We want to build some of the logic structures that are important components of the microarchitecture of a computer, right? Because we're going to build up to the next level slowly. In lecture 9, we're going to talk about ISA, and then we're going to go into microarchitecture, for example. So, what is a logic circuit? A logic circuit is composed of inputs, outputs, and two specifications. Basically, you have inputs, as you can see on the left, outputs coming from the right, a functional specification, and a timing specification. We're going to mainly focus on functional specification in the next several lectures. We're going to talk about timing in lecture 8, as I said. So what is functional specification? I think it's kind of obvious. It basically specifies what the circuit should do, right? What the output should be given the inputs. What is the relationship between inputs and outputs? What is the function that the circuit implements? And this is a Boolean function, as we have discussed, because it's based on binary logic. Okay, timing specification, on the other hand, describes the delay between inputs and the outputs. When the inputs start to change, when do the outputs respond to that change? And when do they stabilize? That's the idea, basically. And we're going to talk about this later. Ignore timing for now. Every circuit has a delay. Basically, the time between inputs and outputs, inputs getting asserted and outputs changing, every circuit has time delay, and we can calculate that delay or model that delay. But that's beyond the scope of what we will do today and tomorrow and the next day. Not tomorrow, next week. Okay, so let's take a look at types of logic circuits. There are actually two types of logic circuits. We're going to cover combinational ones today and early next week. One is combinational logic. Combinational means memoryless. Basically, you don't remember what was done earlier. Outputs are strictly dependent on the combination of input values that are being applied to the circuit right now. You don't remember anything from the past. There is no memory element, if you will. We'll talk about memory elements in lecture 6 when we talk about sequential logic, which is the next type. In some books, they're called also a combinatorial logic. I like combinational much better. It's basically outputs are a combination of inputs, direct combination of inputs. Makes sense, right? You don't have any memory. You can think of your brain having no memory, and you're just reacting to what inputs are coming at this point without any memory that you may have formed in the past. But that's clearly not how humans operate, and that's clearly not how circuits operate. Also, we'll learn about sequential logic, which really has memory in the end. And structure stores history. So you can store what you have done previously, what has happened in the past. And based on that, you can determine the outputs. Not just based on that. Outputs are determined by previous history as well as current values of inputs. That's more like a machine, right? So combinational logic is a good building block. In fact, we're going to build sequential logic using combinational blocks as well. We will see how to do that later on when we discuss sequential logic. But all systems are really sequential, implementing sequential logic. Parts of them are combinational, of course. Okay, makes sense? So let's go into combinational logic. So combinational logic means you really deal with Boolean logic equations. And Boolean logic is really what, basically a Boolean equation specifies the function of a circuit. And let's talk about functional specification a little bit more. Functional specification of outputs in terms of inputs is functional specification basically. That's the function that the circuit implements. But what do we really mean by function? Function, hopefully you've studied it in mathematics or discrete math. It's a unique mapping of inputs to the output values. The same input values always produce the same output value. That should not change. And there's no memory, basically. The output doesn't depend on the history of the input values. That's at least the combinational functional specification that we're going to deal with. Hopefully this makes sense. We're not violating anything fundamental over here. So one example is a full one-bit adder. It's also called a full adder. We're going to see details of it later. But this is basically adding two bits together. A and B are inputs. There's also a carry in, because usually you connect this to other adders so that you can carry input. So sum is the sum of the 3 bits, A, B, C. C is input, carry in again. It's really an XOR function, as you can see. It's the XOR of A, B, C. If you don't believe that right now, we'll later draw the truth table, and truth table will show that sum is really the A, B, C. And C out is the carry out. When you do an addition of two digits, addition of 2 values, you get a carry out for the next addition that you have for the next digit, right? And this is the carry out function. And you can see that these are Boolean equations, right? A XOR B XOR C, and C out is AB. This is really a majority function. So I just gave you the majority function. This is if at least 2 of the inputs are 1, you get a 1 at the end. If at least 2 of the inputs are 0, you get a 0 at the end. So you see two interesting functions over here. One's an XOR, and the other is majority. Okay, and that's your full adder, basically. This is a functional specification, basically. I can throw the specification at you, and I say, this is my full adder. And you can verify that this is what addition should behave like in again, binary. We're talking about binary over here, right? 0 or 1 is, we're not talking about decimal. Okay, so let's take a look at these simple equations, not and or also. So, I mean, we've already discussed this basically. A bar is the output, and you get the not of it, A. And the output is 1 if and only if A is 0. And you can see the truth table, kind of obvious. A and B. Again, the output is 1 if and only if A and B are both 1, truth table. And A or B looks like this. Normally, again, when we do A and B, we can omit the dot. A or B, we normally use plus. That's the terminology, that's the notation. You may have seen different notations. Are you used to this notation? No, okay. You may have seen different notations. Unfortunately, people use different notations in different fields. What do you use for example, in discrete math? That, okay, yeah, exactly. That's, yeah, I think maybe digital design is more practical in terms of bool, because those, yeah, I've seen those also and used them. Okay. Okay, so a big picture of Boolean algebra. Let's go through this quickly since many people know it. It's really an algebra on ones and zeros with and or not operations. What you start with is really some axioms. These are basic things about objects and operations you just assume to be true at the start. And this is just like any mathematical theorem proving, right? And you derive laws and theorems, which we will see some of them. These laws and theorems allow you to manipulate Boolean expressions. Why is this important? Because Boolean expressions are really the functions we're dealing with at combinational logic, and also sequential logic, actually. But let's talk about combinational logic now. That enables us to functionally specify a circuit, but it also allows us to do simplification on Boolean expressions. So you may have a Boolean function. You say, okay, this looks pretty complex. Can I simplify it? What is the minimum expression that is equivalent to this function? Why is this interesting? Because this can actually minimize your circuit. You may, instead of implementing a huge circuit, you implement a small circuit. We will see this, actually. And then you derive other sophisticated properties for manipulating digital designs, represented in the form of Boolean equations. You will see what I mean later on. This may not make sense right now, but for example, we're going to look at max term and min terms, and we're going to specify truth tables based on sum of products and product of sums forms, maybe later today or next week. And you will see that things can be specified in a very simple way if you actually look at it from a Boolean function perspective. How many people have seen things like this? Okay. How many people have not seen things like this? Meaning Boolean algebra, axioms. Okay, maybe you don't remember from your classes, but you probably have seen things like this. Usually I get people who have not seen things like this, so I'm going to cover it. Basically, there's a formality that goes on, clearly. Some of them are not that interesting, but usually binary logic means that, or Boolean algebra means that you have two elements, 0 and 1. And then you have the closure of sets, basically result of and or stays in the set you start with. They're commutative laws. Basically, you can change the order of variables, as you can see, for AND and OR. You have identity elements. You OR something with 0, you get A. You AND something with 1, you get A. And then distributed laws, as you can see, addition. No, sorry, I should say addition. It applies to addition and multiplication also, but but basically, OR distributes over AND distributes over OR, as you can see. These are simple, right? Hopefully, it makes sense to everyone. This is really basic Boolean algebra, and complement is either A is true or A bar is true. Basically, both you get a 1 because A or A bar should be true, but A and A bar cannot be true at the same time, so you get a 0. There's a complement element in the end, and ORing with it gives the identity element, which is 1 and 0 in this case. So basically, you can go through the formalization. Formalization is interesting, certainly, but that's not what we're going to use the formalization for. We're going to use the formalization for writing Boolean equations as well as simplifying the Boolean equations. So we will see that in a little bit. But for that, you really need to know what's going on, basically. Duality is an interesting principle in Boolean algebra. You can convert different expressions to each other. So let's take a look at that. So all of the axioms come in dual form. Anything true for an expression is also true for its dual. So any derivation you make that is true can be flipped into the dual form, and it stays true. Let's take a look at an example. I think more formally, a dual of a Boolean expression is derived by replacing every AND operation with an OR operation, every OR operation with an AND operation, every constant 1 with a constant 0, every constant 0 with a constant 1. That's it. Don't change anything else. Don't change any of the literals. Literals we will define later. But basically, variables, or play with the complements. So example is like this. You have this equation, A and B or C. You can distribute the AND over OR, and you get A and B or A and C. Now, you can apply, this is equivalent to the bottom equation over here, which is you replace the AND with OR, and you replace the OR with AND. And that's what you get, basically. So these are actually dual equations. Okay? This is the dual of a Boolean expression, basically. You get the dual. So why is this important? We will see that. So basically, whatever is true for the for one equation is true for its dual also. So for example, x plus 0, x or 0 is x, right? You get the value of x because 0 is really the element that doesn't have any effect. The dual of this is you change plus, meaning or to AND, like this. You change 0 to 1, and you don't touch anything else, and that equation is automatically true, basically. And you can verify it because x and 1 is x, clearly. 1 doesn't have any effect. This is a simple AND gate, right? Again, you can do it for here, x or 1 is 1, because x doesn't matter if one of the inputs is 1 for an OR gate. And if you form the dual of this, you get x and 0, and that's 0. Basically, we could actually get this without thinking, meaning I change this to its dual, change plus to dot, and change 1 to 0, change 1 to 0, and you get this equation without thinking, basically, because these are the theorems that enable you to operate on equations. Okay, so there are a lot of interesting things like this, but I don't want to really spend time, and because not all of it is interesting also. What you really need to know is how to simplify the equations and how to think logically, right? X or x is x, clearly. It doesn't make sense to say x or x. You can simplify it to x, as you can see. X and x is also x, because x and x, it doesn't matter, ending the same thing. 1 and 1 is 1, 0 and 0 is 0. That's what x and x is equals x means. Involution is complement of a complement is essentially equal to no complement. And you can see that x or x bar is 1. I think I gave you already this, basically. Both of them, either of them must be true in Boolean logic. That's why you get a 1. And here, both of them cannot be true. You get a 0. So this is very logical, as you can see. Commutative law we already discussed. Okay, so there are some useful laws for simplification, as we will see. So this is x plus y plus c. This is the same, basically. Here, the parentheses don't matter. Distributed laws we already saw. But let's take a look at some simplification theorems. And you can actually verify these by essentially creating truth tables, right? That's one way of verifying these theorems. Another way of verifying these theorems is really using logical equations. For example, x and y or x and y bar is equal to x. What do? You basically distribute x over y and y or y bar, and y or y bar is 1. As a result, x and 1 is x. Makes sense, right? And you can also do something similar over here and convince yourself that x or x and y is equal to x. This is actually very interesting. It happens a lot in circuits. And you can also convince yourself that this is true, which I'm not going to go into. So by doing Boolean algebra, you can simplify equations. So this is not a simple equation, basically. You can see that at some point you have a logic gate or a function that looks like this. You can realize that, oh, I don't need to implement logic gates like AND or another AND and a complement. I just have X, right? That's the idea, basically. That's the reason this makes sense to study in digital design, because everything is based on Boolean equations and you can simplify things. And again, duals are also here. I'm not going to go through the duals over here. You can study them yourself, but duals are also correct. If you find an error, let me know what the error is. Okay, so these are actually worth remembering because they show up a lot in real design. Real designs, whenever you design a logic circuit, whenever you simplify, which you will do in the exam, in the in next lecture, for example, but in exercise also, and in real life also, whenever you design a processor, you sometimes see this equation and you basically can easily reduce it. Okay, so prove things. You can clearly prove theorems. I kind of actually showed that earlier without going through the steps, but let's do that. X and y or x and y bar is equal to x. Let's prove it. Basically, distribute x over y and y bar. And then this is 1 clearly. And I base on the identity law, x equals x. So without knowing what the right-hand side is, you can actually derive the right-hand side, obviously. Right? Okay, you can also do it over here, which I'm not going to do. Have people heard about De Morgan's laws? Okay, so many people have. So I'm going to go through this quickly also. I've been doing a lot of quick going through, as you can see. But this is really a transformation. This is what the law is, basically. OR of variables complemented is equal to AND of complemented variables. And its dual is also true. I'm not going to say the dual in terms of logical way. Well, it's very easy to say clearly. But let's say we have a function f equals a plus b plus c. If you apply De Morgan's law, you basically complement it twice. And if this function is true, f equals a plus b plus c is true, then this is the De Morgan applied to it. Logically, you can verify things, right? You can think of things as logical. This means that for this function to be true, at least one of a, b, c should be true. And De Morgan says it is not the case that a, b, c are all false. That's what it means, basically, as you can see, right? So that's the idea of De Morgan. So why is De Morgan nice? Let's take a look at this. So these really are conversions between different types of logic functions. They can prove useful if you do not have every type of gate. So for example, if you do not have a NOR gate, you can still implement things using NAND gates. Or if some types of gates are more desirable to use than others. Some gates are much faster, some gates are much slower. For example, NOR is equivalent to AND with inputs complemented. So this is NOR, as you can see. So this is NOR. And this is AND with inputs complemented based on De Morgan. You can actually follow the truth tables. This is the logical gate. If you don't have that gate, you apply De Morgan, you have this sort of gate. Oh, I have this gate. I can use it in your design. Or this gate is for some reason much faster because of how it operates in CMOS logic. Okay, so keep that in mind. This is also called bubble pushing. It's actually fun. If you see a bubble over here, push it to the inputs and change the gate type from OR to AND. And that's what you get. We call it bubble pushing. So pictorially, you can represent De Morgan as well. So again, NAND is equivalent to OR with inputs complemented. So this is a NAND gate. You don't like it for some reason. You have only ORs like this. Well, use ORs. Again, this is called bubble pushing, right? You have a bubble over here, push it to the inputs, and then change the gate type. That's De Morgan again, pictorially. Okay, I think this is a great place to actually stop, but one of your colleagues wants to make an announcement, so I'm going to give the floor to him, unless there's a burning question you want to ask before he makes an announcement. Okay, no burning question.